overlapping space in this diagram, in the parameter space, but not quite, right? You will see that quite a few of them are on the high magnetic field, longer spin period side. Yes?
Switch it off.
So they are, the population wise, they are similar, but not exactly. And you will notice another thing. In this BP diagram, you see that there is a histogram at the bottom. Can anybody guess what is that histogram about? From the color? Any hint? They are RRATs which do not have any magnetic field estimate, only have spin periods. Okay, so for these objects, I have made a histogram below to show where the spin periods are concentrated. Okay, and you will see that they are concentrated on the longer spin period side compared to the nulling pulsar. So overall, the RRATs seem to be on the longer spin period side. However, the number of RRATs which have magnetic field measurement is small. So we cannot do proper population comparison. The paper that I am talking about and the paper from which this plot is, we have done comparisons, but the results are limited because the numbers are small. So let me show you the results and then I'll tell you what is the next step. And that is the first problem that I will do. So here is a histogram comparison of the spin periods of nulling pulsars and RRAT. The convention which is being followed here is blue for null and red for RRAT, and this dotted black histogram is for everything together. Now, as you can see, that the number of nulling pulsars that we know, all the nulling pulsars that we know the spin period and we know the magnetic field. So nulling pulsars are lovely population, we know everything about them. RRAT, the number is roughly half, and the histogram, the nature of the histogram is completely different, as was pretty obvious from the figure before. The reason for putting all of them together and making a histogram is trying to see if they belong to a same Gaussian population. See, we would be working under the assumption that everything is Gaussian. So forget about what all you have learned before lunch. Now everything is Gaussian. Okay, so you will see that there is a tendency of the combined population to be Gaussian, not quite. There is some hint that this is Gaussian, but it is not. But then you cannot look at a histogram and conclude, right? You have to really do the calculation and try to figure out. So when you do the calculation for the combined population and check whether it is close to a Gaussian, it is not. Even though it looks like a Gaussian, somewhat like a Gaussian, it's not. This is a comparison between the magnetic field and the nulling pulsars. Now here we are really treading on uncertain region because the number of RRATs is too small. the population sizes are not at all comparable. But even then, we can see that the magnetic fields are on the higher side compared to the Nulling pulsars. This is a quantity called dispersion measure. How many people have heard the word dispersion measure? I don't want a hand from you, Rita. Okay, so dispersion measure, we're not going to the details of dispersion measure. It is some measure of the distance of the objects. So there is a suggestion that some of the RRADs behave the way they do, because they are far away. Now, we see that the average dispersion measure of the RRADs is actually smaller than the dispersion measure of the Nulling pulsars. So they are not far away. If anything, RRADs are closer to us. So there have been many suggestions as to why the Nulling pulsar behavior is different from RRADs if they are similar objects. So this was one of the very strong suggestions, but this population, if you look at the population properly, this really doesn't work.
What about the environment? Was it compared to the environment?
These are all isolated.
Clusters, field,
No, they are not in clusters. They are all galactic and they are all isolated. So environment is not really important. Okay, so this is a plot of RRADs at death line. Both Nulling pulsar and RRAD at death line. Now, what do I mean by that? Let's go back a little. Okay, so here are those two death lines, if you remember. Returning back to Rita's question from the morning session, there are quite a few objects below the death line number 2. Okay. So at one point, death line number 2 was the accepted death line. Then many objects were discovered below death line 2. Now people think that 4A might be better. Now, if you ask me why 2, 4A, because there are this list of death lines, they are numbered in some way. And so there's nothing special about these numbers. Okay, so let us say that I take this death line number 4A to be my death line. Let's say I believe in this particular death line. So now, if, let us say, a Nulling pulsar here reaches the death line, keeping its magnetic field constant, where would it go? It's slowing down, right? So it's going towards the right of the picture. So this fellow, if it keeps its magnetic field constant, it will hit the death line somewhere here, right? Okay. I can calculate what that value of the spin period would be at that point, and that is what I am calling as the spin period at death line. Okay. Now you will ask me, why are you keeping the magnetic field constant? We are keeping the magnetic field constant because these are isolated neutron star, and without any other thing happening to them, for such neutron star, magnetic field doesn't really evolve. So I can assume that it will be constant. So if I do that, then the spin period of the Nulling pulsar, the histogram, the blue histogram is the actual spin period histogram of the Nulling pulsars today. And if I take all the Nulling pulsars to the death line, the histogram would be like this pink one. You see, this is really like a Gaussian, and it is very close to a Gaussian. So when they hit the death line, there will be a Gaussian population. When they kind of stop being a pulsar anymore, so that's where they would go. Now, for the RRADs, it's a bit difficult to calculate. because to take a null impulsor to a death line, I need to know the magnetic field. Okay, and I know only the magnetic field of only a few objects. Okay. So this red histogram goes into the magenta histogram, doesn't tell us much. Okay. So we really do not know when they are going to the death line, what exactly is happening in a statistical sense. Now, we can do something else. There have been a suggestion that these RRATs are actually evolved objects from the magnetars. The magnetars, these are the magnetars. These we have not seen before. These stars within circles. And you can see that these objects have much higher magnetic field. So there is a suggestion that these magnetars, their magnetic field is decaying, very strong magnetic field is decaying, and if the magnetic field is decaying, so they will come down, also slow down, so they would take a trajectory like that and cross the death line. So there is a suggestion that the magnetic fields evolve into RRATs. Now, if I look at the possible trajectories of RRATs and possible trajectories of the magnetars, I do not see them crossing. Okay, so these RRATs, because now they do not behave like magnetars. When I say behave like magnetars, what I mean, I'll explain in a moment. So now these RRATs would be moving to the death line like this. RRATs would be moving like this. There might be some crossing, but as a population, we don't see that all these RRATs have come from a population which is there. Okay. Now this figure is from this paper that I have been mentioning here, and this was done by Abhishek, Namrata, Gayatri, and Tanushree, 2020 batch. So this is published and everything. So this is where we left the problem last year. Here is another paper which also has a Hyderabad connection. So this is done with the student Tanmay Chauhan and Professor Sharmishta Manik from BITS, Hyderabad. And there we did evolution of magnetic fields. We did not look at population. What we did, these red dots are magnetars and the blue dots are high magnetic field radio pulsars. Ordinary regular radio pulsars, but have very high magnetic field. We looked at the evolution of their magnetic field with some physical parameters, some extended range of physical parameters. And this pink region is where the evolved magnetars will come after a while. And the blue region is where the evolved strong magnetic field radio pulsars would come. Now they do not touch the death line really, this is the death line. They do not touch the death line because to evolve all these objects up to that point would have taken a very long time. And Tanmay didn't have that much time, so we cut it off. But you can see the regions and which objects they are spanning very clearly. These yellow circles are the RRATs. Okay. So which population are the RRATs expected to come from? They are likely coming from the high magnetic field radio pulsars. They are, the final sort of, what should I say, the deathbed version of the strong magnetic field radio pulsars. That's what it looks like. Now, let us define what is it we can do at this stage. Now, what is the main problem with RDAS? The main problem with RDAS is we do not have too many measurements of the spin period and the magnetic field, right? Now, one thing we can do is we can sit here and say, okay, wait for 5 years. Let us see how many more RDAS we see, how many measurements we have, and then, redo this calculation. But we can do something better with the data that we have. The first problem with RDATs. So let me show you the RDATs. Just give me a minute. Okay, this is the RDAT catalog. Now this is my personal file, so this is not what is public yet. It would become public within a week or so. So here what we have done is consider this column, which is the spin period, and this column, which is the magnetic field. Now in the column of spin period, you will see many blanks. There are very many blanks in this column, but even in this column, there are many blanks. That means we know a particular object is an RDAT, but we do not have a period measurement. So you will ask me why. It is because of this reason. Suppose I see a pulse now, and after time t1 I see another pulse. After time t2 I see another pulse. After time t3 I see another pulse. So t1 minus t2 is my first pulse interval. That, let me call that delta 1. t2 minus t3, my second pulse interval. Let me call it delta 2, and so on and so forth. Now these delta 1, delta 2, delta 3s are not equal. Okay, which some, one delta 1 could be 5 seconds, delta 2 could be 2 days, and so on and so forth. Okay. So what is the period? How do I get a measure of the period? I say the real spin period must be the greatest common factor of all these deltas, right? So maybe the pulsar, let us say that the pulsar has a spin period of 5 seconds, right? Now every 5 seconds I'm supposed to get a pulse. Suppose 3 pulses are absent, I get a pulse after 15 seconds. Suppose 7 pulses are absent, then I get a pulse after 35 seconds. Okay, so I get various numbers, and then I look at the greatest common factor among them. I find 5 seconds is that number by which all of these intervals are divisible. And then I say, so that must be the real spin period of this object. And this is how most of the RDAT spin periods have been calculated. Now, there are sometimes uncertainty, because please remember, when I say 5 seconds, 10 seconds, 5 seconds are on the larger side. So all RDATs, as you have seen, there are many RDATs which are much smaller spin period. And if you get a train of data to correctly figure out what is the pulse interval, and all the pulses may not have similar strength. So sometimes, something is faint or something. So therefore, it may not be very accurate. And when it is not accurate, there are signatures to understand that this calculation may not be accurate. And at that point, a correct spin period is not quoted. So investigators do not quote a proper spin period if they feel that this number may not be correct. So then Therefore, even if we know that this is an R rad, it has shown certain spin periods and so on, certain pulses, and we have characteristics of the pulses which are very similar to rotation powered pulsars, we still cannot correctly calculate its spin period. So that is problem number one. Now this we cannot do anything about. Now, as I have explained to you in the morning, the magnetic field, the estimate of the magnetic field is coming from the derivative of the spin period. If I can't calculate spin period very accurately, how am I going to calculate period derivative? It's even more complicated. Even for objects for which spin period has been calculated, getting a spin period derivative is very difficult, because what you need to see is you need to see a trend. The spin period is slowly changing over time. If you do not have a large number of pulse observations, then even if you have an estimate of the spin period, you may not have a proper estimate of the period derivative. And therefore, we have even less number of objects for which magnetic field estimate, that spin period derivative estimates are available, and period derivative estimates are available. So this is where the problem lies. So what are we going to do with this? First of all, what we would try to say is that all these objects for which spin period calculations are available but period derivatives are not available, these are prime candidates for investigation. Why? We know something about them. It's not that we do not know anything. If we know the spin period, then, and seeing that they are still functioning as pulsars, what can you say about them? About their magnetic field? Can someone make a guess? You know the spin periods and you know that they are functioning, not very well, but functioning as radio pulsars, similar to radio pulsars. What can you say? Any guess? They have to be above the death line. Okay, maybe very close to the death line, but they have to be above the death line. Okay, so that much we can say about their magnetic fields. They have to be above the death line. Okay, so therefore, if I, let us say, I assume that the 4A line is my death line, I'm taking that as my death line. So therefore, all these objects should have magnetic field above this value, whatever is the corresponding value. What else we should do? So we have got a lower limit for the magnetic field, right? Magnetic field has to be above. All right. Then there is one more thing we need to do. We have also seen that it is likely that they have come from magnetars. Are they magnetars? Because we know some magnetars from which we get radio pulses. Now you will ask me, what are these magnetars? You keep saying radio pulsar and magnetar. So what is the difference? Now for radio pulsars, we have seen that the emission is coming from the magnetic dipolar radiation and the energy is coming at the cost of the rotational energy. Yeah. What are magnetars? In common parlance, many people define magnetars as having very large magnetic field. Let's go back to that picture. Yeah, right? These are the magnetars. But I would say that definition is not really correct, because there are, you see the Magnetars here, very large magnetic field. Now we do have radio pulsars, some of which also have very strong magnetic field. So that is not the distinguishing feature at all. What is the distinguishing feature? First of all, observationally, we do not really see radio pulses from them. What we see are sporadic X-ray bursts from these objects. Okay? So that is observationally. Intrinsically what happens is, if you look at these X-ray bursts and you calculate the luminosity, X-ray luminosity, doesn't matter if it is X-ray. So calculate that luminosity, so you have an idea of the total energy radiated per time from that object. Now, if you calculate the rotational energy derivative, the dEdt that we were talking about, I omega dot, because you can, for magnetars, you can calculate omega and omega dot. So if you calculate that rate of energy change, dEdt, you will find that the luminosity of the magnetars that has been estimated from observation, that exceeds the rotational spin down energy change. That means that simply because this fellow is slowing down and some energy is coming out, that energy cannot explain the luminosity of the magnetars. So magnetars, yes,
Luminosity and radio X-ray.
excellent. See, for the radio pulsars, the radioluminosity is a small fraction of the dEdt, rotational dEdt. So there are many pulsars which emit in all the frequencies which have been observed. Most pulsars emit in a range of frequencies. Radio is the easiest to observe. So for radio pulsars, there is no problem. The radioluminosity is just a small fraction of the total energy available, the dEdt that is available. In case of magnetars, the situation is reverse. The luminosity that we are seeing is larger than the dEdt available for us. So therefore, we must have another source of energy. And this is where strong magnetic field is important, because the one source of energy that neutron star can tap into is the decay of this extremely strong magnetic field. So if the magnetic field decays, you have some amount of energy, and actually that is really huge amount of energy. A small fraction of that is sufficient to explain magnetar luminosity. So that is the basic difference between radio pulsars and magnetars. They have different kind of energy source. Okay, all right. So first of all, we have to say that how are we going to track the magnetic field of this RRADs? We have found the lower limit, right? Now we are going to say that we have seen that from the known objects that magnetars seem to be evolving into RRADs. So therefore, now that they are RRADs, they are probably not magnetars, which means their energy should be coming from the spin down itself. They should not require a magnetic field decay. All right. Now this is theoretically very nice. Huh? Yes. So this is lovely. Okay. What do we need? We need the luminosity of the RRADs. No, radio, X-ray, wherever. We don't have. Okay. So let me show you. So this is like, I love this because this feels like we are doing some detective investigation. What is this?
History.
Mystery, yes.
Prove it is.
Yes. Herbal Poirot. All right. So this is, go there. Now this is our main workhorse, ATNF Pulsar catalog. You will get your data from there, and you build your models depending on that. And here I should mention that this is also a little time in coming. Two students from the 2020 batch, Rohit and Satyajit, they they have created a Python package which goes into all these pulsar repository, neutron star repositories that I was showing in the morning. So this Python package takes a query for a particular object, goes into all these repositories and grabs all the information that is there and gives you. So they still have some glitches to fix, and they're telling me it will be up very soon. It's one version is already on GitHub, but they haven't made it public because not entirely happy with the thing. So this is another 2020 product, a lovely product. If it comes, Pulsar community is going to love it. So I'm very hopeful that they would fix the glitches quickly. So this is the ATNF catalog, and anybody who wants to do any kind of pulsar work needs to do this. So you will get all kinds of data from this. Not that every object would have a value for every parameter they have. Many objects have that people have not looked into all those values or haven't been able to get the values. So that's okay, but you will get a huge number of values. Unfortunately, some of their plotter is not working since last few days. Otherwise, I would have showed you some quick plots here itself, but the plotter is not working. Anyway, so what we are seeing is the number of RRATs. Now ATNF has a list of RRATs, but their list is not exhaustive. That's the problem. Anyway, so these are all RRATs. This is the spin period. This is the magnetic field value which are available. I have only dragged those objects which have magnetic field and spin period. And you see the column for radioluminosity is nothing. None of them have any radioluminosity estimated. Okay? All right. But if you look at the rotational energy available here, the dEdt, that is from about 10 to the power 32, 10 to the power 32 ergs per second. That's roughly the number. Now these numbers are important. Let us go and try to look at some values for the magnetars. So I'll have to change it to magnetars. Again, there are no radioluminosities. Of course, the magnetars are burst in X-rays, but now you will see that the dEdts are actually larger. Even with larger dEdt, their X-ray luminosity cannot be explained. Okay, so therefore, it's obvious that some other engine is there. But the important point is the DDT is different amongst between the uh, magnetas and the RLATs, that's all fine. But unless we know radioluminosity, we really do not have a handle. It's just DDT, the total energy that is available. So one thing we can do is, let me go back to the RLAT thing. Let me take this out. So let me show you all the RLATs. See, there is this huge number which do not have any parameter value estimates. These are all RLATs, that's all we know. No spin period, no magnetic field, no nothing. And here are all these objects. So there, at least the DDT available is different. So this is one value that we can take. So if we say that all the RLATs that we know about, let us assume that the maximum DDT available to them is equal to the maximum that we know today. What is the maximum value of DDT of the RLATs that we know? I saw 32 somewhere. Right, this value. Can you see that? It's very close to 10 to the power 33 arcs per second. Huh? Can I zoom? I did not do that. Ah. Right?
Yeah.
So there was this, right, this value. So it's something like 8 into 10 to the power 33, almost close to 10 to the power 33, which is actually taking in it to magnetar level, but it's an upper limit. Okay, so let us say that we are saying all these RLATs for which we do not know the magnetic field, let us equate their DDT to this value. Then you will get a magnetic field value for them, and that will be the upper limit for the magnetic field. Okay, so now again let's go back to that picture. Here, so these are the fellows that we are talking about. So one, the lower limit of the magnetic field is this, and the upper limit would be coming from a luminosity. Let's arbitrarily set it as 10 to the power 33 arcs per second, which is the maximum. So that gives me the upper limit of the magnetic field. So for, as you can see, because the spin periods are different RLAT from this group would have different upper limit for the magnetic field, and of course different lower limit for the magnetic field, because this, let us say something with this spin period has a magnetic lower limit of the magnetic field here, whereas this fellow would have a magnetic field there. Okay, so now we have, for each spin period we have an upper limit and a lower limit. Okay, so we have created a band, generated a band within which these RLATs should be, in order for them to function as a sort of like a radio pulse. Now what we should do? This is something that I wanted to flash, is that there are a number of very slow radio pulsar with strong magnetic fields which are being discovered recently. Now this is an object, Gleam X, it has a string of numbers after this, do not worry about it. This fellow, there was a lot of uncertainty and controversy about this, and this is the object for which I had this explanation that maybe the magnetic field is something like 3 into 10 to the power 16 Gauss. And as you can see, this is really, really high, but some of the Russians are also saying the same thing, so I'm happy. And also, here is on this is 1000 second, the spin period is 1000 second. This fellow, discovered a little later, has a spin period of about 80 seconds. And there is another one which is not in this figure, which is sitting in between. That also does not have its magnetic field estimated. So these are not magnetars. Even though very strong magnetic field, really, really large magnetic field, but these are radio pulsars. They behave like radio pulsars. Some, their characteristic is somewhat different from radio pulsar here, which is expected because the magnetic field is very, very strong. But they are radio pulsars. They are not magnetars. Some of them are radio magnetars in the sense that they are actually magnetars, but we see radio pulses from them, but they are magnetars. So we have large period, strong magnetic field, radio pulsars, which are not magnetars. And it is also possible that some of the RLATs might be coming from there, because we, in this problem that I have shown before, yes, here, we looked at some of the strong magnetic field radio pulsars from this region and tracked their evolution. We have not really looked into the evolution of strong magnetic field radio pulsars that are there. When we started this problem, those fellows were not discovered, so we didn't know that there would be strong magnetic field objects sitting here. Okay. So RLATs could also be coming from those. And one of the sort of holy grail of neutron star astrophysics is finding evolutionary connection between different classes of objects. So this is one, why, what are RLATs and why are they behaving the way they are? So very tempting explanation is that they are coming from different, they are evolutionary products of maybe magnetars, maybe just high magnetic field radio pulsars. Our calculations, at least at this point of time, it suggests that they are coming from high magnetic field radio pulsars, not magnetars, but who knows? No? The data is not yet large enough. So what one can do is look at this set of RLATs. Now we have found ways of getting the upper limit and the lower limit. So one of the possible ways of looking at this RLAT population is, for each RLAT, you have an upper limit and a lower limit. So, and you have this about 100 RLATs for which magnetic field is not known, for each of which you have an upper limit and a lower limit. What one can do is take an object, run a random number generator, pick one value using the random number generator between the upper limit and the lower limit, and that gives you a possible spin period magnetic field pair for a given RLAT. So you do that for 100 objects. So then you have this 100 RLATs with known spin period and a possible value for the magnetic field. So then you have, and you also have another 100 RLATs for which we know So there is 200 RRADs, 100 we know both spin period and magnetic field, other 100 we only know the spin period, and we are creating a population. This is an artificial population in terms of the magnetic field. So we have created a 200 object RRAD. Now what we can do is, now we can go and do a proper population comparison with the nulling pulsars. Does that give me a good result? No. Because we have used a random number generator and picked an arbitrary value of the magnetic field between the upper limit and the lower limit. So what should I do to get a realistic answer to my problem?
Going for the random numbers, within that range, you can go for the mean.
Then you are basically putting them on a line, right?
We should look for a common number which is divisible to all periods intervals.
No, that is for periods. We are looking at magnetic field, means we are going into period derivative. There such an argument does not work. Two deadlines? No, two deadlines. I am using one deadline. See, these two deadlines are historical. People first had one deadline, then there are too many things below them, so people created another deadline. So if I am working with deadline, I have to take one. Any suggestions? Any guesses?
Come generate again and again
Again and again.
and see the conversion.
Yes. You do this for these 100 objects. So you create one population, then another, and see where it converges. And then compare it with the nulling pulsars. And then really see where the calculation goes. Because the result of this particular paper, Abhishek and company, is very counterintuitive, extremely counterintuitive. That it still is counterintuitive in the sense that these 200 objects, all of them have a dispersion measure, and the dispersion measure is saying that RRADs are closer to us, not farther away. Farther away would have helped. No, they are very far away, so sometimes they are fainter and then we don't see them. No, they're closer. On the average, they're closer to the nulling pulsar. So it's already counterintuitive. But now if we can do this and see where our results converge, that would give us a very strong and robust answer without waiting for another 10 years for observers to give us the numbers for period derivatives. Does this problem make sense? So this is the first problem. Okay. When is D?
30 minutes.
Huh?
Maybe it's 3:30.
Okay.
Okay.
But you
So,
started late, not you started late.
no, it's fine. Because I do not want to start now. Tomorrow's problem is completely different.
Yeah. Okay.
So we'll.
It's 37.
Good. So tomorrow we will talk about objects. So before we disperse, so today we were talking about objects here, this side. Tomorrow we will talk about objects there, the millisecond pulsars, and the experts are sitting there. They have been working on millisecond pulsars for quite a few years. They know everything about it. Okay? All right. So that's that for today.
We're back here at 4 o'clock for Desh. Yeah, Desh is at 4.
And then Desh needs to leave at 5:15. So please don't come late. Yeah, because he has to join and then
I will log out.
yeah. Okay, this is